Hello listeners, welcome back. So today we have reached to the last theorem of our discussion. So today we'll be discussing about maximum power transfer theorem. So maximum power transfer theorem states that maximum power is transferred from a source to a load when the load resistance or impedance is equals to the complex conjugate of the source internal resistance or impedance. So that means in case of this DC circuit as we have drawn here, so maximum power will be transferred when RL equals to RS, where RS is the source resistance. And in case of AC circuits, it will be ZL equals to, since it is complex conjugate, so it will be complex conjugate of source resistance. So this we'll again discuss whenever we start with our AC circuits. So this ZS complex conjugate is, suppose if we have a signal x plus jy, this is given as ZS, so the complex conjugate would be x minus jy. So this is what complex conjugate means, and as per the maximum power transfer theorem, so maximum power will be transferred from source to load when the load resistance equals to the source resistance. Now it becomes slightly tricky because whatever circuit we draw or whatever circuit we solve, not every circuit is like this, of this format, right? But if we think it deeply, that as per the Thevenin theorem, what it states, any complex network can be converted into a simpler network containing a voltage source and a series resistance, right? So the voltage source is given by VTH and series resistance is given by the RTH, where RTH is the internal resistance of VTH, because we measure both of them across same terminal, right? So since as per Thevenin theorem any circuit can be converted into this, so maximum power transfer is valid for every circuit. And when maximum power will be transferred, whenever RL equals to RTH. So let's see how this is possible, how this can be proved. So now before going into that, so why do we require actually maximum power transfer theorem? So for example, like in communication, audio or RF systems, matching impedance ensures maximum signal strength without distortion or reflections. Similarly, in battery or generator system, it helps to determine the ideal load for extracting the most power, right? So to understand the trade-off between power and efficiency, when maximum power is transferred, efficiency is only 50%, and that is the half of the power is lost in the source. So this power helps the engineers balance between maximum power and maximum power efficiency depending on its applications. So that means maximum power transfer theorem is applicable in various applications or various fields, and to do it properly we should understand how this maximum power is transferred. So now coming back to how RL equals to RTH. So to do that, let us consider first the circuit that we have drawn here. So let me erase this area first and get some space. So to start with, let's consider this circuit. So in this circuit, the value of current I will be given as V divided by RS plus RL, right? Now power delivered across the load will be equals to P equals to, we already know it is I square RL, so which will be, if I put the value of I here, then it will be V square RL, and this is RS plus RL whole square, right? Now in place of RS we can also write this as RTH and this VS as VTH, right? So let us change them. So this is VTH and this RS is represented by RTH, okay? Now what we know, when maximum power is transferred to the load, it is given by dP DRL should be equals to 0, right? So now if we put this value of P here in this equation, then we have DRL of VTH square. I am putting RL here, and this will be RS plus RL whole square. Now this is in the format of U by V, so ddx of U by V format. So after expanding the differentiation, so it will be like this: RS plus RL whole square minus of after differentiating we have 2RL whole multiplied by RS plus RL, right? So I hope you are following up to this. Now coming to the lower term, this will be RS plus RL whole square of the whole square, so it will be to the power 4. Okay, so now equating this whole term into 0, so we have RS plus RL whole square minus 2RL RS plus RL equals to 0. Now after breaking this term, we'll have RS square plus RL square plus 2 RS RL minus 2 RS RL minus 2 RL square equals to 0. So this term, after cancelling, what we have is RS square equals to RL square, so that means the value of RL should be equals to RS, right? So now here what we consider about, in the first equation we have considered RS equals to RTH, so this is equals to RTH. So what we find is maximum power will be transferred where RL equals to RTH. So if we represent it by a graph, so this is the representation here as it is shown here. So this is the value of RL versus we have power here. So maximum power will be delivered when the load resistance is equals to source resistance RS or RTH. Okay, so maximum power is delivered when RL equals to RTH. So this is maximum power transfer theorem. Now if we want to determine the maximum power, so that will be, so P max equals to IL square RL. So IL is nothing but, from the Thevenin circuit we have it as VTH divided by RTH plus RL square into RL. So this upper term is VTH square. Since RL equals to RTH, so we can write it as twice of RTH whole square into, this is also RTH. So finally what we are going to have is VTH square divided by 4 RTH, right? So maximum power is given by VTH square divided by 4 RTH. So this is the formula which we will be requiring during solving the numericals. Okay, so let us consider a numerical now, how to apply this on numerical. So today while we are considering a numerical, we will be considering a problem which will consist of various concepts, like which we can encounter during solving of any circuits like Thevenin, whether it be Thevenin or Norton or reciprocity or any other circuits. So we will consider the maximum amount of conditions that can be available in any numerical. So let us see how to solve this one. So in this circuit we have to determine the value of load resistance at maximum power transfer for maximum power transfer, and then determine the maximum power. This is the question. So that means we have to determine the value of RL, and as per the maximum power transfer theorem, we know that value of RL equals to RTH. So we have to determine RTH and VTH, right? So if we see, let me first take one more copy of the circuit. Okay, so what we have to do here is we have to determine VTH and RTH. So for determining VTH or RTH, what we have to consider is we have to remove this load and determine the value of VTH and RTH here. So if I consider, then this two terminal will be, suppose this will be positive, this will be negative. So we have to determine VTH. Now if we see the circuit diagram, then this circuit contains 1, 2, 3, 4 mesh or 4 loops, right? So out of those 4, this VTH, the loop which containing this VTH is open circuit. So that means there will be no current flowing in this circuit, in this loop, right? So that means we have 3 loops. So there will be 3 equations, right? Plus along with that, whenever we go for determining the RTH, then as you can see in this loop we do not have any series or parallel connection. That means all the connections are mixed up, and it is slightly difficult to determine the value of the equivalent resistance. So if we see it, so if you check, then this 5 ohm and this 10 ohm are in series, so we can combine them together. So it will be 5 plus 10 is, so we have a 15 ohm resistor here. Similarly, this 18 ohm and 9 ohm are in series. So what we can do, we can minimize them into 9 plus 18 is 27 ohm, right? Now circuit is slightly reduced and there is no change in the current or any conditions, right? So now if we see it thoroughly, then this is a shape of a star, this is also in a shape of a star, right? So sorry, this is in a shape of a delta, right? Triangular shape. So now it will be slightly difficult to determine the equivalent resistance because we do not have any series or parallel connections here, right? So if we convert this delta into a star, then let's see, our circuit becomes slightly solvable, right? If you can see it here, now this will be our corresponding circuit after converting into star. This will be the circuit. Then if we convert it like this, then our circuit will be easier. So let's convert it then. So after converting, suppose since we have all the resistance at 15 ohm, so if we solve for one resistor, suppose RA, this is suppose RB, RC. So if we solve for RA, the remaining two will also be same, since the resistance values are similar. So the value of RA will be given as, we already know the formula, it is the sideways whichever resistance we have, multiplication of them divided by the addition of all the resistances. So if we solve this, this will come out to be 5 ohm. Yes, okay. So similarly for 27 ohm, if we consider, suppose we are considering it as Rx, Ry, Rz, then it will be 27 into 27 divided by 27 plus 27 plus 27, so which will be 9 ohm. Okay, so our new circuit will be this resistance. So this is our star. So we have 5 ohm, 5 ohm, this is also 5 ohm, and then we have RTH or VTH here. Then we have this resistance, below resistance, which is 20 ohm. Then we have here a star of 9 ohm. And the remaining circuit is we have a 100-volt supply. Now the circuit becomes very easy, which is having now only a single loop, right? So we have here only a single loop, right? This loop is we have only this loop. So if we have one loop, then the solution is very easy now. So if we determine the current, so we will be writing the KVL equation. So KVL will be 100 minus, so this will be 100 minus 5i, then minus 5i, then minus 20i, then minus 9i, then minus again another 9i equals to 0. So the value of I will be coming as 2.08 ampere. Okay, now if you want to write down the equation for VTH, so for writing down the equation for VTH, so what we have here is, so we can directly write down considering the loop. So in this loop we can consider the outer loop, this loop we can consider the outer loop, and then write down the equation. So if we consider the outer loop, then it is 100 minus, we have 5 here, 5i, then there will be no current here across this 5 ohm and 9 ohm, but we have the voltage drop. So the voltage drop is minus VTH, since we are moving from positive to negative. Then this is minus of 9i here equals to 0. So we have the value of VTH as 70.88. After solving we get this. Okay, now similarly if you want to determine the resistances, then this is our circuit. We will be short circuiting the supply. So this will be our circuit. We have these three resistances are in series, right? So let me write down the values. This is 5, this is 5, this is 5, this is 20, this is 9, 9 and 9. Now if we see it properly, we can minimize it like this. So we have the upper 5 here, this is our RTH, and this is upper 9, 5 ohm, 9 ohm. Then we have one 5 ohm resistor and one 9 ohm resistor, like this in this path. And in the second part we have these two parallel paths, right? This is one these two are parallel. So we have 5 ohm here, 9 ohm here, and finally all these three resistance in the middle, they are in series. So we have here 5 ohm, 20 ohm and 9 ohm. Now after solving, these three are in series, these two are in series, or then these two are in parallel, and then all the circuits are in series. So 5, 9 and this will come out to be 9.92 ohm. So after combining all these three, because they are in series, so value of RTH is 23.92 ohm. Okay, so this is RTH, this is VTH, we have already obtained. So now the value of, as per maximum power transfer theorem, value of RL equals to 23.92 ohm. Value of VTH we have already obtained, 70.88 volt. So now the maximum power can be calculated as P max equals to VTH square divided by 4 RTH, which is 70.88 square, divided by 4 into 23.92 equals to 52.51 watt. Okay, so these are our answers after solving. Okay, so I hope this is understood what is maximum power transfer theorem and how we can solve this. Okay, so now as we know, we can convert any circuit into a Thevenin circuit, so we can apply the circuit which contains dependent sources also can be converted into a equivalent Thevenin circuit. So in the next class we will be discussing the circuits for maximum power transfer theorem and when we have a dependent source, right? So I hope you have understood up to this, and this is very much easier. So like in Thevenin theorem, first part is for maximum power transfer theorem is the first part. What we have to do is we have to convert the circuit into Thevenin circuit and then apply the maximum power transfer theorem, maximum power formula, which is VTH square divided by 4 RTH. So that's it. Okay, so thank you for joining. So we'll be meeting for the next class very soon. Thank you.